Hello, ladies and gentlemen. In this video, we are going to consider a series of finite and countable sets. What do we have? We know how one can compare two sets for having the same number of elements or one set being greater or equal than another set. For this purpose, we use injections and bijections. But now we want to formalize an intuitive concept of the number of elements in a finite set. First of all, we are going to define finite sets. How is it possible to do so? There are different approaches, but one we are going to apply is the approach based on labeling some simple sets as exemplary finite ones. So for every natural number n, we will consider the set n underlined, or sometimes I'll call it just n. What is it? It is a set of first n naturals, all such natural numbers which are less than n. It is easy to see that there are no naturals less than 0, hence 0 underlined is the empty set. 1 underlined consists of just 0, hence it has exactly one element. 2 underlined is 0, 1, and so on. And in general, n plus 1 underlined is n underlined, the set of all elements which are less than n plus n itself. You know, m is less than n plus 1 if and only if m is less than n or m equals n. So this is this line is another way to state this equivalence. Okay, and we shall say that a set is finite if and only if it is equivalent to at least one n underlined. So a set A is called finite. It is called finite if and only if there exists a natural number n such that A is equivalent to n underlined. Of course, it is quite an interesting question whether there may exist distinct numbers n and m such that for both these sets n underlined and m underlined we have that A is equivalent to them. Is it possible? Intuitively, it is not possible, but how can we prove it? Of course, if we consider some particular numbers, we can prove it by a brute force approach by considering all functions that say there is no bijection between 3 underlined and 2 underlined. So how one can have, say, an injection? Here lies the problem, an injection from this set to this one. Yeah? If we try to construct one, then what the value of this function, of this putative bijection between 3 and 2, what can it be? Assume that it takes, say, 1 at 0 as an injection. Our function f must take 0 at 1, but what about 2? In fact, there is no possibility for our function to take a value at 2. But what can we do for some abstract, arbitrary numbers n and m? So, okay, let me reiterate. Intuitively, this number n will be the number of elements, we shall define the number of elements in A as this number n. But of course, here we have a question. Is this number n indeed unique? So is it possible that n underlined is equivalent to a, while m underlined is also equivalent to a, but m and n are distinct numbers? Is such a situation possible? Of course, it is not possible, but this requires a proof, and the respective proof is not that hard to obtain. We shall prove it using induction. Okay. For every n, for every natural number n, for every function from n plus 1 to n, f is not injective. F is not injective. So it is not possible to find an injection from n plus 1 to n underlined. So there is no way to obtain such an injection. How can we prove it? We shall assume that there is such n and there is such an injection. And then we shall take the least such number n. So here lies our application of induction. By the least number principle, let us take, let's take the least natural number n such that there exists an injection from n plus 1 to n. So our goal is, of course, to obtain a contradiction. Formally, we have assumed that there is such a number n, and we have taken the least such natural number n. Okay, the first case, as it is usual in arguments by L and P, we consider two cases when n is either 0 or when n is something plus 1. Okay, assume that n is 0. If n is 0, then we have an injection from 1 underlined to 0 underlined. But 0 underlined is the empty set, while 1 underlined is not empty. So f is a function from some non-empty set to the empty one. Hence, the value of this function at 0, it must exist, hence f is total. This value is an element of the empty set, which is clearly impossible. So we have obtained our required contradiction. Now, the second case is when n is some m plus 1, where m is a natural number, of course, which is less than n. So now assume that n is something plus 1. So what do we have? We have that n plus 1 is embedded into n via our function f, but look, as m is less than n, and n was the least strange number, so we have that m plus 1, which is the same as n, m plus 1 is not embeddable into m. For no less a number, our strange injection is possible. Okay. Now let us consider this injection f. So we have n plus 1, which is the same as m plus 2. It contains 0, it may contain 1, it necessarily contains m, it necessarily contains m, and m plus 1. And m plus 1. And in n underlined, which is m plus 1 underlined, we have elements from 0 up to m. So f is 0 is mapped somewhere via our function f. 1 is mapped somewhere, and so on. But now let us look at m plus 1, at the greatest element. After all, anything except this element is just our set m plus 1 underlined. Yeah? This greatest element may be mapped anywhere in general, but assume that we are lucky. And this element is mapped into M. Assume. What do we have then? Look, that means that all the other elements are mapped where? They are mapped here. And here we have the set M underlined. All elements which are less than M. And we have found an injection. So here we were lucky. The image of M plus 1 was just M. Then if we take formula, we shall take the so-called restriction of M plus 1, of F unto M plus 1. What is it? It is our set F, the set of arrows, intersected with M plus 1 underlined multiplied by whatever, say by n. What is it? It is the set of all such arrows except this one, except this last arrow. So we are taking all pairs, all arrows from our function except the last one, all arrows starting at m plus 1. So this function, let's call it f prime. F prime is clearly a function from m plus 1 to m, and f is injective. So we see that m plus 1 is embeddable into m. A contradiction, because m plus 1 is not embeddable into m. Our luck was in that m plus 1 is mapped into m. But what if we are not that lucky? So then, in this case, all the remaining arrows comprise an injection from m plus 1 into m, which is not possible. But what if we were not that lucky? What if f mapped m plus 1 into some other point, Let us consider this general case. We are not that lucky. So let x, whatever, be the value of f at our last point m plus 1. And now I'll show how one can reduce this general case to the case we have already considered. So still we have n plus 1 underlined, which is m plus 2, and here we have 0, maybe 1, and so on. M plus 1. This is a set m plus 1 underlined. And everything here is allegedly injectively mapped or embedded into m plus 1 underlined, where we have all the elements from 0 up to m, and this part, excluding our last point, is just m underlined. So, and somewhere here, we have our x. Somewhere here we have x. Somewhere here we have x. So x is the value of f at m plus 1. So my idea is quite simple. I want to swap x with m. So we shall define another function which will be called g. This function g essentially swaps m and x. So what is it? Our g is a function from n underlined to n underlined, which is defined the following way. It takes m if its argument is x. It takes x if its argument is m, and otherwise it just does not change its argument. It is quite clear that our function is a bijection. Clearly, G is a bijection between n underlined and n underlined, and in particular, it is injective. So let us consider our old friend f prime, which is the restriction of f unto m plus 1 underlined, or n underlined. So what is it? It is a set of all arrows starting here, somewhere in n. The set of all such arrows. Let us take this function. It is injective, so this function is injective, as f is injective, and g is also injective, of course. Being a bijection, it must be injective. Okay, and now our next step is to take some other function, some composition. Let h be just the composition of f prime and g. What is it? Look, f prime is a function from n underlined, of course, to n underlined. This is quite clear. So here we have a composition of two functions from n underlined to n underlined. Or in other words, it is a function from m plus 1 to m plus 1. And this function is injective. As a composition of two injections, this function is necessarily injective. It is necessarily injective. So we have an injection h from m plus 1 into m plus 1. My last goal is to prove that, in fact, h does not take this value m. My statement will be as follows. M does not belong to the range of h. Okay, from the contrary, assume that there indeed exists some k in m plus 1 underlined, of course, such that h of k equals m. What do we have then? What is h? H is a composition of f prime and g. But this term equals g of f prime of k, and in fact it equals g of f of k, because f prime takes just the values of f, not all such values, but every value of f prime is a value of f at the respective point. It is a restriction. But when g takes value m, you know, g takes value m if and only if the argument equals x. So that means that f of k equals x. So we have that f of k equals x, and on the other hand, by the definition of x, we have that f of m plus 1 equals x. As f is injective, we see that k equals m plus 1. But on the other hand, k was strictly less than m plus 1. So we have got a contradiction. It is quite clear intuitively that m is not a value of h, because the value of m is possible just at m plus 1. We have just proved this easy thing. Aha! So I see that m is not in range of h. So what does it mean? As a result, we see that h is still an injection of m plus 1 into m, because the only element that differs m plus 1 from m, namely m itself, it doesn't belong to the range of h. So we have constructed a forbidden injection from m plus 1 into m. Such injection is not possible, so we have obtained a required contradiction. What have we just done? We have reduced the general situation when the value of f at m plus 1 is some x, some arbitrary x, to a situation when we are lucky and when it is immediate, how one can make an injection from m plus 1 into m from a given injection from m plus 2, that is n plus 1, to m plus 1, that is n. So we have just swapped x and m. If you think about it, you shall see that it is trivial, it is almost obvious. So far, we have proved that for no natural number n, there may be an injection from n plus 1 into n. And slightly generalizing this statement, we may obtain the famous Dirichlet or Pigeonhole Principle. In Russia, it is better known as Dirichlet's Principle, after a prominent French mathematician Dirichlet. But in the English-speaking world, it is usually called the Pigeonhole Principle. This principle says that for arbitrary naturals m and n, if m is greater than n, then there is no injection from m underlined into n underlined. Or in Russia, they usually state this principle for school children as follows. Assume you have m rabbits and n cages, and the number of rabbits is greater than the number of cages. Then you cannot put these rabbits into these cages injectively, that is, in such a manner that no cage contains more than one rabbit. So it is an injective function if you assign a cage to a rabbit. No two distinct rabbits are assigned identical cages. So it is not possible to have an injection from a greater amount to a lesser amount, but please be careful. Here, greater and lesser means that we have sets of the form M and N underlined. So in other words, equivalently, you can you may restate this principle the following way. Whenever M is embeddable into N, then M is less or equal than N. So this principle connects two concepts of less than, one for sets and one for numbers. How can one prove this principle? It is very easy if you have lemma 1 at your disposal. So assume that M is indeed greater than N, and M underlined is embeddable into N underlined. What we have? Then N plus 1 is less or equal than M. As it is less or equal than M, so as it is less or equal than M, then N plus 1 underlined. N plus 1 underlined is a subset of M underlined, but we know if it is a subset, it is of course embeddable. So what we have? We have N plus 1 underlined being embeddable into M underlined, which is embeddable into N as being embeddable. Embedding is transitive, hence N plus 1 is embeddable into N, contrary to lemma 1. It is not possible to have an injection from a greater set to lesser set. And dually you can restate it with surjections, corollary. For every M and N, for every two naturals M and N, if, say, M is less than N, then there is no surjection. Okay, let's call it F. There is no surjection. There is no surjection from M underlined to N underlined. So there is no surjection from lesser set to a greater one. In terms of rabbits, if you have M rabbits and N cages, and you have less rabbits than you have cages, there is no way to put the rabbits into the cages in such a manner that every cage is occupied. There are no empty cages. There is no way to assign cages to rabbits surjectively in such a manner that every cage is used, every cage is occupied. How can one prove it? It is not hard to reduce it to Dirichlet's principle. Okay. Assume that we have some number M which is less than N, and in fact there is a surjection F from N underlined to N underlined. What do we have here? So M underlined and N underlined. N underlined is greater. Let us consider an arbitrary element x here in n underlined. As f is surjective, for every x, there exists some k in m underlined such that f of k equals x. This is just surjectivity. And our task is to take one of them. Let us take just one of these k's and define a function g which will map every x to some k with this property. In fact, working with numerical sets, we can define it more in a clearer way. So let g of x be the list k in M underlined such that f of k is x. Oh, it is now clear that g is a function from n underlined to m underlined. It's easy to see that it is functional and it is total because f is surjective. What else? For every x, f of g of x, according to this definition, equals x itself. So g of x is the least such a number that f of that number equals x. So f of g of x always equals x. That means that the composition, such a composition equals the identity relation for n. Okay. Now my statement will be as follows. G is injective. G is injective. Why is it injective? Assume that g of x equals g of y. What do we have then? Then, of course, f of g of x equals f of g of y. But on the other hand, f of g of x is just x and f of g of y is just y. So we have proved the required thing that x equals y given g of x equals g of y. So g is in fact injective, hence g is an injection from n into m, but look, n is greater than m, n was greater than m, so we have obtained an injection from a greater set to a lesser set, which is not possible according to the Pigeonhole Principle. Okay. So we have no surjection from a lesser set to a greater set, and we have no injection from a greater set to a lesser set. And these things give us another interesting corollary, which we will prove at our seminar class. It is left for seminars. Okay. If A and B are finite, if A is equivalent to B, and A and B, of course, is finite, and let me state it more symmetrically. Assume that we have two finite sets which are equivalent to each other. Then every function from A to B is injective. It is injective if and only if it is surjective, that is for B. Every injection from A to B is also surjection. That means that every injection is bijective, and every surjection is bijective. That is between two finite sets of the same size, which are equivalent to each other, which have the same number of elements, injections and surjections are the same. So let us consider an example of using this statement. It is very common in mathematics. Assume that we have, at HSC, we have 11 possible grades for students from 0 up to 10. Yeah. Assume that we know that 11 students. Assume that 11 students have taken the exams, and we know that these students were marked injectively. That is, no two distinct students had identical marks. Then every mark has been used because there were 11 students against 11 marks. So they have assigned their marks injectively, hence surjectively, and every mark has been used. On the other hand, assume that these students were marked surjectively, that is, every mark had been used. Hence, our marking function, assignment of marks to students, was injective. Hence, no two students were sure that no two distinct students had identical marks. This argument sounds very intuitive, but it is worth noting that this is not valid for infinite sets. No such thing for infinite sets. For example, we may consider a function f from naturals to naturals, which say maps every natural number into the next one. So clearly f is injective, but f is not surjective, as there is no x where there is no n such that f of n equals 0. So this property is a distinctive feature of finite sets, and in fact you may take it as a definition of finite sets, but nevertheless we prefer to have it as a theorem and use another definition. But now we have to come back to our definition of finiteness. Still, we haven't yet proved that this number n, such that n underlined is equivalent to a, is unique. But now we shall do just that, applying the Pigeonhole Principle. Corollary 4. I say that for every two natural numbers m and n, if m doesn't equal n, then there will be no bijection between the two. Okay, let us prove it. Assume for the sake of contradiction, assume that m equals n, but m underlined is nevertheless okay. No contradiction is required. M doesn't equal n. So then we have two cases. Either m is less than n, or m is greater than n. And according to our theorem 2, to the Pigeonhole Principle, there is no injection, as m is less than n, there is no injection from n to m underlined. And here we have, as m is greater, we have no injection from m underlined into n underlined. But in neither case, a bijection is possible, because if they were equivalent, there would be an injection, but there is no one. Yeah? So for distinct n and m, the required m under the corresponding m underlined and n underlined are necessarily not equivalent. Hence, for every finite set, there exists a unique such natural number n, that a is equivalent to n underlined such number is unique. This number n is called the cardinality or size of the set A. We write it this way. So these bars surrounding A, this equals n. The size of A equals n, and in fact, this size is uniquely defined. It is a property of A. You cannot have distinct sizes. In Russia, we say мощность instead of cardinality. Of course, you can call it размер, but it is slightly less popular in Russian usage. Okay. For every finite set, we have just one such number n underlined. And this number reflects the intuitive concept of the number of elements in n. Or, let us add it here, or the number of elements in A. Okay, let us give another definition. What does it mean that a set is infinite? A is called infinite. Please pronounce it correctly. Not infinite, but infinite, because it is influenced by Latin pronunciation. It is called infinite if and only if it is not finite. A is not finite. It is not finite. It is quite clear. And another definition, A is called countable. Countable, from the word to count. It is called countable if and only if A is equivalent to the set of naturals. In a sense, countable sets like that of naturals will be the least infinite sets. We shall discuss it later. So infinite is just not finite. Countable means equivalent to n. Okay. And now let us develop a series of finite and infinite sets. Excuse me, of finite and countable sets. So lemma 6. If A is equivalent to B, and A is finite, or say infinite, or countable, then B is such as well. It is as well finite or infinite or countable, respectively, because you see that all these concepts were defined in terms of equivalence. It is obvious. No proof is necessary. It is obvious. Okay. But we have a question. Is it the case that a countable set is not finite? Maybe it is finite. What if? What if it is finite? For this case, we have the following theorem. If A is countable, if it is countable, and B is greater or equal than A in terms of embeddings, and A is embeddable into B, then B is necessarily infinite. In particular, every countable set itself is infinite because it is embeddable into itself. So everything where a countable set is embeddable to is necessarily infinite. Assume that B is finite. What does it mean? Then there exists some natural number M, the cardinality of B. So then B is equivalent to M underlined. But what do we have? We have that M plus 1 underlined, of course, is a subset of N, while N is equivalent to A, as A is countable and A is embeddable into B, while B is equivalent to M underlined. Of course, here we have embeddability. So M plus 1 is then embeddable into M, contrary to our lemma 1, contrary to the pigeonhole principle. So every set whose part is countable is necessarily infinite. It is natural to ask, is it the case that every set, every infinite set has such a countable part, a countable subset? It is true, but this requires some work, some additional work, and in fact, it requires stating a special axiom, the axiom of choice. In fact, some weak version of the axiom, but this is out of the scope of our course. Okay. But look, from the previous lecture, we should know that it cannot be proved or disproved whether we have anything strictly in between naturals and reals. But do we have anything strictly in between finite and countable sets? So it is fundamentally undecidable whether we have anything between countable set and the continuum. But do we have anything in between finite sets and countable sets? In fact, we have nothing. This can be proved using induction, but the rigorous proof is quite technical. So I will give you just the very idea. So if A is a subset of N, if A is a subset of naturals, then A is either finite or countable. It is either finite or countable. So every subset of naturals is either finite or countable. There will be no proof, but just the idea. So the idea is as follows. Let us sort A in an ascending, that is rising, growing in an ascending order. What does it mean? That means that we want to count all the elements of our set in such a way that they shall grow in an ascending order. So we shall arrange them this way. Apparently, it is possible. So then we have two cases. The first one, we run out of elements of A. What does it mean? That means that for some n, we have something like that. Then A is finite. We have a bijection between A and n underlined. Another case, we never run out of these elements. Then we have what? We have that for every natural number, there is a respective element of A. As they are ascending, we have no identical members in this sequence. So that means that A is equivalent to n. So we have a function f, which maps n into an. And here we have the converse of it as our bijection. That's it. But of course, a rigorous definition of this sorting is it requires some effort. It requires some effort. So it is not just a proof, but a proof sketch. So we see that every subset of naturals is either finite or countable. And as a corollary, we may obtain the following statement. If A is embeddable into B and B is countable, then A is either finite or countable itself. Or if something is less or equal than a countable set, it is itself finite or countable. It is itself finite or countable. How can one prove it? It is almost obvious. Look, we have that A is embeddable into B, and B is indeed countable. So what do we have? Then A is embeddable into N. So A is in a one-to-one correspondence, in a bijection with its image, which is a subset of N. So by our previous lemma, A and its image are either finite or countable. It is quite clear. Another corollary. A is finite or countable if and only if A is embeddable into a countable set. Look, if it is embeddable into a countable set, it is finite or countable, and vice versa. It is almost obvious. Every finite set is equivalent to some n underlined, which is embeddable into the set of all naturals. Yet another corollary. What if we have a subset, or more generally, something embeddable into a finite set? If A is embeddable into B, where B is finite, then I say that A is finite as well. And moreover, for finite sets, we have the cardinalities. So the cardinality of A is less or equal than that of B. This is particularly applicable to the case when A is a subset of B. If it is a subset, it is embeddable. So a subset of finite set is necessarily finite and has not greater cardinality. How can one prove it? It is still quite easy to do so. By corollary 9. So let A be embeddable into B, and B finite, that is, be equivalent to some n underline. Yeah. So clearly M is embeddable into n underline. So A is embeddable into a countable set. So by corollary 9, A is either finite or countable. May it be countable? No, it may not. If A is countable, yeah, then we have that n underlined is embeddable into M. Yeah. But everything, if something is embeddable into finite set, it is okay. So what do we have? We have that. Let us repeat the argument we already had. Then M plus 1 underlined being a subset of n must be embeddable into M underlined, which would give us a contradiction. So that means that A is indeed finite. Let us consider its cardinality. Let us take this unique n such that A is equivalent to n underlined. I want to prove. My goal now is to prove that the cardinality of A is less or equal than M, the cardinality of B. For the sake of contradiction, suppose that N is greater than M. What do we have then? You know, A, which is equivalent to N underlined, is embeddable into B, which is equivalent to M underlined. Yeah. So we have that n is embeddable into m underlined. But on the other hand, that means that m plus 1 is less or equal than n. That is, m plus 1 underlined is embeddable into n underlined. So we have, which gives us a contradiction with lemma 1. Aha! So everything which is less or equal than a finite set is itself finite with a lesser or equal cardinality. In particular, we may consider, say, intersections and differences of a set. If A is finite, then the sets A intersected by B for whatever B and A minus B are finite as well. Moreover, the cardinalities of these sets are less or equal than that of A. As a proof, you may cite the fact that A intersected by B, this intersection is a subset of A, and A minus B is a subset of A, so then you can apply our previous corollary. Every subset of a finite set is finite itself and has not greater cardinality. So look, ladies and gentlemen, we proved that two operations, namely intersection and difference, subtracting a set, they do not lead us out of the world of finite sets. The difference of two finite sets, the intersection of two finite sets are also finite, always. So this realm of finite sets is closed under these two operations. But whether it is closed under other set theoretical operations, like union, product, Cartesian power, or power set. Let us explore these problems. The first of those is the well-known rule of sum. The rule of sum is one of the most basic combinatorial facts. It essentially connects properties of addition, a numeric function, a function over numbers, with the properties of union of finite sets. So let A and B be finite. Let us consider two finite sets which are also disjoint. This is an additional property we will get rid of. Let us consider two finite disjoint sets. Then I say that A union B, another set, is also finite. And moreover, its cardinality equals the sum of the cardinalities of A and B. So here we are reinterpreting addition numeric addition in terms of set union. I'll use well-known properties of addition without a proof here, but of course, in a more elaborate theory, one should first prove by induction, most likely, the required properties of addition and then transfer them onto finite sets. Okay. Assume now that we have a bijection F between A and some n underlined, and another bijection G between B and M underlined. So n and M are cardinalities of A and B respectively. What do we need? What is our goal? Our goal is to construct a bijection H between A union B and this set, n plus m underlined. We need such a bijection. How can one construct it? Aha! Let us define our function h this way. H of x will equal f of x when x equals a, when x belongs to A. And if x belongs to B, we may take maybe g of x. No, of course not, because in both A and B, we have an element corresponding to 0. So we may have an element corresponding to 0. So this time we will obtain not an injection. But in order to make it injective, we shall just add n to this value. What do we have? Clearly, for every x from A union B, this h of x is greater or equal than 0. Its values are natural numbers after all, and it is less than, it is always less or equal than n plus, it is always less than n plus m, because this value is less than n, that is plus 0, and this value is less than n plus g of x, while g of x is always less than m. So indeed, that means that h is a function with values in n plus m underlined, but whether it is injective or surjective, that is the question. H is indeed injective. Let us prove it. Assume that h of x equals h of y. What is required? Clearly, to prove injectivity, it is required that x equals y. Here we have 4 cases. The first case is when both x and y belong to A. After all, you know, x and y belong to A union B. The first case is when both elements belong to A. Then h of x is just f of x, while h of y is just f of y. So we may use the fact that f is injective and obtain x being equal to y. The second case is when x belongs to A and y belongs to B. What should we do then? Then h of x is just f of x, while h of y is n plus g of y. So we have that f of x equals n plus, but we know due to arithmetics, we know that this number is greater or equal than n. Due to arithmetics, we are freely using arithmetical arguments. Here is greater or equal than n, while this number is necessarily less than n. because f, after all, is a bijection between a and the set of all numbers less than n. Ha! Clearly, we have that n is less than n, which is impossible due to arithmetic. So this case is not possible. Another case when x belongs to b and y belongs to a. This is similar. This is similar to the second case, and the only remaining case is the fourth one. Here both x and y belong to b. Then we have that h of x equals h of y, which is n plus g of x, or n plus g of y. Of course, it is almost immediate that we can both sides, but think a little bit about that. Here we are also exploiting an arithmetical theorem that if n plus k equals n plus l, then k equals l. So by arithmetics, due to an arithmetical fact, g of x equals g of y. As g is in every possible case, we have obtained that x equals y, hence h is indeed and now let us prove surjectivity. H is surjective. What do I need? I want to prove the following. For every number k from L underlined, there exists x in either A or B equals k. How can one obtain this number? By the way, why was it important that A and B were disjoint? This was important for functionality of this function. You know, x either belongs to A or to B, but not to both these sets. Okay. What do we have about this k? You know, k is between 0 and n plus m. So arithmetics, we have two cases. Either k is less than n, or k is greater but still less than m. We have two cases. For the first case, I can call surjectivity of f in and obtain an element x in A such that f of x equals k. You know, f is a bijection between A and n. We have such an element x. And this f of x will be h of x, as x belongs to A. But what should we do in the alternative case? In the alternative case, we shall apply another arithmetical fact and subtract n from all the three terms in this inequality. So we shall 0 minus n being less than m. And now an x in B such that g of x equals a minus. But then g of x plus n, still due to arithmetics, Well, and on the other hand, this equals h of x. So in both possible cases, we have obtained an element where the function h takes the value k. Hence, h what we need. Hence, we have proved our theorem. And this theorem was a translation of facts about addition into the language of bijective correspondences of equivalent sets. Now, as a final point of today's lecture, let us generalize this rule of thumb to the case when A and B are finite, but not necessarily disjoint. Our last statement, corollary 14, if A and B are finite, with no additional requirement of them being disjoint, then their union is finite. And moreover, the cardinality of this union equals the cardinality of A plus the cardinality of B minus the cardinality of intersection. How can one prove it? The main idea here is to reduce this statement to the previous one, that is, consider disjoint sets. Okay, look, what is A union B? Clearly, A union B equals A minus B union B. This set is finite by definition, by the assumption. Why is this set finite? It is a subset of a finite set. Hence, it is finite as well by a respective corollary. You know, previously we had corollary 11. If something is embeddable into a finite set, it is finite itself. So by corollary 11, we have that these two sets are finite, and needless to say, these sets are disjoint. So, by theorem 13, by the rule of thumb, we have that this set is indeed finite, and its cardinality, its size, its number of elements, equals the sum of the number of elements in this difference plus the number of elements in B. But now let us compute this value. What is it? Look, A equals A minus B. Here it is, by the way. A minus B union A intersection B. These both sets are finite. This one is also finite as a subset due to corollary 11. These two sets are finite. The intersection is empty. So by another application of theorem 13, we have that the cardinality of A equals the sum of these two numbers. Using a little arithmetic, we obtain that A minus B, the cardinality of A minus B is just the cardinality of A minus the cardinality of intersection. Now let us combine these two formulas. If we combine them using still more arithmetic, we may obtain the required resulting formula. So here we have cardinality of A plus cardinality of B minus rearranging it to the end of this formula, we have this one. That's all. So for every two finite sets, the union is necessarily finite with this cardinality. And in particular, if A and B are finite, then the cardinality of the union is always less or equal than the sum of these two cardinalities, but in fact greater or equal than the greatest between them, the maximum. Because A is a subset of the union. That's all for today. But our next point, the next point we are going to explore is as follows. Assume that A and B are finite. What can one say about their product? The operation of union does not lead us beyond the scope of finite sets. But what about product? In fact, the product of two finite sets is always finite, and the cardinality of this product equals the product of two cardinalities. This is another reason to call Cartesian product a product. For finite sets, it is closely connected with the numeric multiplication. Okay, thank you. Please be careful. Please focus on our results, at least the statements. Memorize these lemmas. They are important in everyday business of combinatorics, of counting something. Of course, you may take these results intuitively, but it is way better if you have derived them from some basic axioms, exactly as we have done. Thank you, ladies and gentlemen. Have a nice time.